Well, it turns out that the type of waveforms that are discussed in terms of like Class A, Class B, Class AB, and Class F depicted here, those are really only meaningful at the intrinsic ports of the transistor inside of the parasitic resistances and capacitances, which when present will actually distort these waveforms. So when we think that we've achieved a Class F amplifier, we need to be looking at the intrinsic waveforms to do that. More information about understanding the what and why of intrinsic IV waveforms can be found on this link that is shown here in the QR code for a collaborative blog article that we had done with Qorvo. Let's turn our attention to stability, and those of us who've had RF courses in our undergraduate, maybe graduate courses mostly learn about stability factor, and the K factor analysis is very popular. It's really useful primarily for two-port networks and has limitations. Matt will discuss some of those. What is indicated for what is called unconditional stability is this parameter K being greater than 1, and it has to have an accompanying parameter, for example here indicated by B, being greater than 0. So you need two conditions, and then if K is greater than 1 and B is greater than 0, you can say the device is unconditionally stable. And what that means, we'll discuss a little bit more. Again, it's a measure, useful, but not always sufficient. From that point of view, there's another parameter, because those two parameters might be a little inconvenient to have to carry around two parameters. Dr. Lee Edwards had, and his colleague there had written a paper where there's one single parameter, mu prime, which is also available within ADS, that you can look at as an indication of unconditional unconditional stability, again, from a linear point of view. Now, what unconditional stability means is that there should not be an impedance that you can put on the input port with your input matching network or your output matching network that would cause the opposite port to exhibit a negative resistance. That's a simple description. Let's look at an example analysis of a QPD 1028 Qorvo transistor selected with a model selected from the library. And we just set up a simple S parameter analysis here where we drop in the mu prime calculator parameter, the stability measure, and stability factor. We put in the maximum gain, which is useful to look at. We also dropped in the load stability circles and source stability circles, which we'll look at in a minute. We set the impedances here to 3 ohms instead of 50 ohms because it gives a more useful graphical depiction of what's going on. Better S21 gain. So this is a little bit, these impedances are a little closer to what we have to match the transistor to get some good gain out of it. The maximum gain is shown in this plot in red, and the S21 for 3 ohm source and load is shown in the blue. If we look down below here, we've plotted the stability factor K that we've talked about. That is shown in red, this one, and it reaches a value of 1 at 480 megahertz, and above that, it stays above 1, and the stability measure is shown in magenta here. That's the B parameter we looked at before. That stays positive, so we can say in terms of the classical unconditional stability criteria that this device is potentially unstable below 480 and unconditionally stable above 480 megahertz. We also plotted the mu prime, and that's also consistent, so that also achieves 1 and stays above 1 above that frequency. I mentioned the source and load stability circles, and those are shown in this graph where we can see that the circles in the source plane, we always have to do a test, and without getting into the details here, I can tell you the test we have to do when we have a circle. The circle is actually closed outside of the Smith chart, but these are circles or contours, which are parts of circles. And we always have to do kind of a test to find out at a particular frequency whether it's the inside or the outside of the circle that represents the unstable region. And what I can tell you is that for this case, in both the load and the source plane, it's going to be the inside of the circles, or in other words, the center of the Smith chart in both cases, which actually represents a 3 ohm impedance, is going to be a stable point. So these are going to be the stable regions at all frequencies. What the circles mean is that inside those circles, if you were to match GAMS-SABES, for example, inside the circle at that frequency at the opposite port, you would expect there to be a negative resistance, meaning in looking into the drain of the device. Same thing over here. If we matched here at M1, for example, at 240 megahertz, what we would expect is at the input port, we'd expect that looking into the gate of the transistor, we would see a negative input impedance, negative part of the real part of the input impedance. One of the things I dropped in, and one of the things we're going to talk about more today is the WS probe. And so the WS probe is a probe developed by Dr. Tom Winslow at MACOM, and there's several stability analyses that go beyond the K factor and U prime analysis that we talked about here. Matt is going to get into those in a moment. I want to just introduce this probe a little bit by giving you at least one tie-in to how we can relate it to the K factor and stability circle analysis that we just looked at. Among the other features of the WS probe is you can use it as a probe to look to the left and look at what impedance is being presented looking to the left and to the right with ZG and ZL. If you happen to notice in the previous schematic, I actually had dropped in a WS probe at the input and another one at the output. And so if we look at the ZL of this input probe, it will actually be looking into the gate of the transistor. If we look at ZG of this output probe, it'll be looking into the drain of this transistor. And so if we now consider this in the context of these stability circles, I am going to show you two cases that I considered. I analyzed redid the analysis by first starting with the way this simulation is set up with 3 ohms here and here, and I looked at the output of this probe analysis, and that's shown here on the left. What we see is that both looking into the gate and the drain, the real part of the impedances stay positive. That's a good thing. Then the next thing that we did is we set the matching conditions to be inside of the stability circles here, and we redid the analysis. So set the source to 0.3 plus J 1.5 and the load to 0.3 plus J 0.3. And now we have both the impedances indicating looking into the gate and looking into the drain. We have negative resistance here at some frequencies. Okay, so that is kind of consistent with the meaning of the stability circles and the K factor analysis. And of course, this only happens at low frequencies. You might be wondering what's going on here. I mentioned earlier that we have included, for all the transistors in the Qorvo GaN library, we've put these WS probes at the most intrinsic part of the transistor. So if you take one of the models and you push in, include the gate to drain capacitance. So instabilities arise due to feedback, and if you only have your probes at the outside of the transistor, as we would have in this case, there might be an instability caused by the feedback inside the transistor that you might be missing. This helps you maybe get around that limitation. Okay, with that, I want to turn it over to Matt Ozales of Keysight, and he's going to take you farther into more advanced stability analyses. And I did want to mention that if you are interested in the Qorvo GaN library, you can access it through this link here or this QR code. And you can also request a free trial of the Monolithix Complete library, which includes all types of passive and active models that you might want to use elsewhere in your circuit, for example, in your matching circuits and bias circuits. The combination of these two work very well together for successful board-based PA design. Thank you.
All right, well, thank you, Larry. For my section, I am going to be presenting a simple process for rigorous stability analysis. So the agenda that I'm going to cover today, we're going to start out with an introduction to the stability problem. Larry kind of already set this up. Then we're going to look into some historical perspective going all the way back to the days of vacuum tubes. And we're going to try to pull out of that some modern transistor implementations for these older tube techniques. And then I'm going to introduce a new probe to simplify the stability computation. And then finally, I will present the simple process for rigorous stability analysis. And then if there's time, I'll get into a couple advanced topics. Okay, so first I just want to frame the problem. For many years, if you look at the way stability was handled, essentially, we would do design, we'd get a part back in the lab, and it would be unstable. And then the RF engineers would go through the process of fixing it. So they'd go into the lab, they'd change components, they would shave transmission lines, do anything they could to stabilize their circuits. This was all pretty standard. But things are changing in the industry, and what's really happening, we can see it at Keysight even. This is one of our instruments, and if you look inside the instrument, you know, previously we had the design here in the middle of the screen. This is a wire bond and thin film design. So if you have a good technician or you're good with your hands, you can go in there and make adjustments to potentially stabilize one of these circuits. But recently we've moved to wafer level packaging, and this is where we stack all of the chips in these micro packages, and nobody can get into this to fix it. So the reality is we have to fix stability problems not in the lab as much anymore, but we have to actually address it in the design process up front. And so that's what this talk is really going to be about. Getting to the problem with K-factor, so we start here where Larry left off, and the issue that we have with K-factor is that it's not rigorous, and it's not going to work sometimes for these more complex circuits. And the classic example of this is this resonator, the ring oscillator from Struble and Platzker that they introduced in the 1990s. So this is a very simple circuit. I've set it up in Keysight Advanced Design System. And what we can do is apply a very, very small step function to the input here. So I've got a step. This voltage goes from 0 to 1 nanovolt. And we're going to apply a transient simulation. And when I apply this transient simulation to the circuit, if I observe the output, you can see that it starts oscillating quickly to 100, then 200, then into the megavolts range in only 20 or 30 nanoseconds. So this circuit is clearly extremely unstable. However, if we look at the traditional K-factor for this circuit, we can do that. The K-factor comes out to about 90 at its lowest point, and it has a valid response. So essentially the K-factor here is wrong because this circuit is extremely unstable, and that's really the problem. So that gets into this idea of, well, if that doesn't work, then what technique should I use? And, this slide is supposed to look complicated. When I went and looked at this, if you do a search in IEEE database for stability analysis, you end up with all these papers, and they're hard to untangle. It's kind of like this tangled web of techniques. And the reality is that, no one technique that's come out really works for all of these different things. So what I'm going to try to do in the next few minutes is just untangle some of these techniques. Like, where did they come from? What's the history behind these techniques? And so to understand that, we have to really go back to the beginning, which was at Bell Labs. A lot of the work that we're going to apply to the stability process now was actually done in the 1920s to 1940s by three key engineers who you probably know their names already if you're working in this field. Let's go back almost 100 years to August 1927 and talk about Harold Black's invention and application of negative feedback. This is actually the drawing that he had. He drew this on a napkin while he was on a boat. He kind of had this epiphany about feedback in circuits. And so he wrote this paper about negative feedback amplifiers and realized that there are a lot of good things that can come out of applying feedback in amplifiers. And interestingly enough, the origins of the company that I work at, Keysight, was HP. And so HP, Hewlett and Packard, did a lot of work on this concept of feedback and to design these circuits because they were designing oscillators. And so this is one of the first HP products. This is the 200A. This came out in 1939, and it was an audio oscillator. And essentially, the application for it, it's kind of interesting. It was used in the Disney movie Fantasia. That was the first HP product that was done. And this idea of feedback, we still apply it today in stability analysis, and this is done using what we call loop analysis. So loop gain or loop analysis, this is still very, very useful technique. If you've taken an analog circuits class, you've already seen this technique. Essentially, on the left-hand side, this describes it. So we have a signal that comes in, and it goes through a gain block, and then it comes back around through a feedback network, and comes back and adds with the input. That's basically the way this feedback circuits work. So if we want to characterize the loop gain, all we have to do is break the loop. So we just cut it. If it was in the lab or in the simulation, we would break the wire. Second step is we'd inject a signal on one side and we'd observe the return on the other side. And then we can plot like the gain and phase. So this is something that a lot of people learn with op-amp types of circuit designs. And the thing that I want to point out is for RF microwave circuits, if you've done op-amp design, you're used to these like really predictable responses for gain and phase. These are things like Bode plots, which we all learned in school. But if you're looking at it for an RF amplifier, you're not going to see such a nice response. You're actually probably going to see more of like a weird spiky response for both gain and phase. And that's because these circuits aren't designed in such a predictable way. A lot of times the feedback loop in the RF microwave circuits, they're coming through unpredictable or unintended paths. And so we don't really have control over these feedback loops. There are a lot of different ways that we can do loop gain. All of these make different assumptions. I just put 4 techniques here that are very, very widely used in the industry. Ostest, Hurst, Middlebrook, and Tian bilateral loop gain approaches. And of these, probably the best approach that's ever come out up into this point, if I only had one loop gain technique to use, I would use this bilateral loop gain technique. Essentially, this uses a set of stimulus, a voltage and a current source stimulus that came from Middlebrook, but it extends that to be a bilateral signal flow because signals can flow forward and back in a loop. So I'll get to that in a minute. But every single loop gain technique makes assumptions, which can invalidate the results of the technique or can make it only work well for certain conditions. The other point that I want to make down here on the right is that this is really fundamental, but when we think about something like phase margin, I think a lot of people get confused because when we do Bode plots and we have phase margin, we think of 180 degrees as being the problem area. But remember, that's for an op-amp. So the signal goes through a negative terminal in the op-amp, which shifts it another 180 degrees. And that means that the signal that comes back through is actually 360 degrees out of phase, which results in constructive interference. I just want to point out that for RF amplifiers, we do have some differential amplifiers, but for single-ended RF amplifiers, that's not the case. We don't have a negative feedback path. The feedback is additive. It's coming back. So we need 360 degrees of phase shift through that loop. So just taking the Qorvo GaN device with the Monolithics model, we can do this type of loop gain approach, right? I have a device here and I broke the loop at the drain of the device, and then I injected a signal into the drain, and I looked at the loop gain and I got essentially 0. This is a common problem. This is something that designers do all the time. They make kind of a mistake here. So the question is why? Why is there no loop gain here? And the reason is because if you trace the signal paths, there's really nowhere for the signal to come back. So if I put a signal in on this green arrow, it's always going to end at one of these ideal ground symbols, which we all know that doesn't exist in real life in the lab. But for the purposes of simulation, that just ends the signal, that terminates the signal. So there's no path in this case for the signal to travel somewhere and then come back where it started. And that's what we need to have loop gain. But we can fix that. One of the things that Larry talked about is we've got intrinsic access to some of these devices. So we can actually go in and look at the loop gain intrinsically for these devices. And so, for example, I can go into this device and I can break the connection between the feedback capacitor, between the gate and drain here. And when I do that, I can measure the loop gain effectively inside of the transistor. And when I look at that, I get a very, very different story. You can see now I have positive dBs of loop gain that's increasing as I go up in frequency. So this is fundamentally why transistors can be unstable when we present it with the wrong load. If we were to put the wrong load on here, we could essentially resonate this stability loop and cause an instability that's happening inside of the transistor, still due to loop gain and feedback, but not visible from outside of the device. If we break the loop outside of the device, we see nothing. If we go inside, we break that loop, we can see now the fundamental cause of instability. So this is a really important concept for loop gain. We have to be able to break the loop to observe it, and that's not always possible. All right, so I want to go back to our history discussion here. And if we go back to the 1940s, so we started at 1927 with Harold Black. Now we're going to go up to the 1940s. And what engineers were starting to realize was that this this gain feedback model that Harold Black proposed, it was a little bit simplistic and it was starting to break down under certain specific conditions. So very astute engineers like Heinrich Bode, they were realizing that like other effects were happening in this case. So one effect is that, feedback just does not only go in one direction, and gain does not only go in one direction. It turns out these things are what we call bilateral. That's like what I mentioned with Tien's loop gain. So Bode was really looking for something a little bit more fundamental. He was looking to address this type of a problem. And his goal was actually to get a definition of feedback that was rigorous, or like this mathematical definition of feedback to overcome the limitations of this like circuit level loop analysis that was happening, which oversimplified the problem. So that's what Bode set out to do when he wrote his book, Network Analysis and Feedback Amplifier Design, in 1945. He was looking for a fundamental mathematical general definition of stability. And the way he did it was kind of ingenious. He actually looked at electrical networks as in two different ways here. On the left-hand side, he looked at an electrical network as a set of nodal equations. So essentially, if you take any node inside your circuit and you just isolate that one node, you can view it that as like the rest of the circuit drives it. So the response from the rest of the circuit is driving that node. And in that case, you can look for negative impedance conditions or energy sources. And he did that using the driving point impedance. You can also look at a network a different way, which is that gain feedback approach that was taken earlier. But essentially, Bode defined this idea called the return difference. And essentially what he did was he created a stable denominator in this circuit in this analysis by removing the gain from the denominator term. So he looked at the system determinant over the system determinant where the gain aspect was removed. And if you know anything about instability, it arises from a combination of gain and feedback. So essentially what Bode was doing here was guaranteeing that the denominator was stable in this circuit, and that allowed him to know for sure that the results from this, if he was looking at encirclements for this, would indicate the unstable plane, the right half plane poles, which is really what he was looking for. So just jumping ahead to the modern day, we can still apply these techniques, and work has been done to modernize and apply these techniques. So starting with the return difference in the 1990s, Wayne Struble and Aria Platzker did a lot of work on building this normalized determinant function. Essentially what they showed is that the same analysis works if you have one active gain source, or you can zero out if you have multiple active sources. You can zero them all out at once simultaneously and arrive at the same results that Bode was able to achieve. So in a modern circuit, what we can do is we can go up into the intrinsic active device node, and we can put probes across that so we can monitor the admittance network of it. So like if you had S parameter terminations, you'd make these really high valued, like something like 1 × 10 to the 12th ohms, so that you're not loading down the circuit internally. And then you can use a function to convert the S to a Y value, and then you can take the determinant of that Y network. This would be a 4-port Y network, so you can compute the determinant of that in a straightforward manner. Well, you can do the same thing if you just turn the source off. So in this case, I can just go into the current generator, I can set it to 0, and then I can redo that exact same analysis with the circuit off, and then I can look at the encirclements, clockwise encirclements around the origin, and I can then determine, if I count those encirclements, essentially how many unstable poles there are in this circuit. And so this is known as the normalized determinant function. And this is a way to determine the global stability of a circuit. So if you do this across all of the active nodes, you turn them on, you turn them off, you take the determinants, you can get the global stability of the circuit. So this technique is kind of like, been the gold standard of how to analyze your circuit for stability. And it works really well. There are some challenges with it. One challenge is that you need to go into the intrinsic node and actually get in there and turn it off. You can't always do that. The other challenge is that it converges at infinity, at frequency of infinity, essentially. So if you're doing an EM simulation, that's part of your feedback network, that's contributing to your instability, you may need to do EM simulations to very high frequencies with this technique. The other approach that Bode described is the driving point impedance. So we can do that in the modern days with what's called an auxiliary generator. Essentially, we apply like a current source to a given node in a circuit, and then we can determine the impedance of that node, and then we can look for what's called Kurokawa's oscillation condition, which is essentially when the real part of the circuit goes below zero. So we change from an energy dissipator to an energy source, right? And the imaginary part has to be zero as well. Essentially, we're guaranteeing that no energy is stored in the rest of the circuit. So this can be done in a straightforward manner. However, the downside to this is that it only applies to the node that you're looking at. So it's a way to determine stability for just one node. So if you have a lot of nodes and a lot of active device, you have to repeat this analysis over and over again to get a bigger view of your circuit. So that's it. That essentially brings me to the simple, effective approach for stability here, which is, look at the intrinsics, use a rigorous technique, NDF or driving point at minutes, see if your circuit's stable. If it is, consider all the loads. If it's not, look for loops. And that's the way to move forward. The problem here is that the setup is way too complex. So we're using all these different types of analyses, but if you look at the circuit setups to do these types of analyses, they're all different, and it requires you to manipulate your circuit in all these different ways. For example, you may need to go into your intrinsic, node and put probes across it, or you might need to put a current generator over there, or you might need to do two separate perturbations of your circuit to derive a loop gain. So this is a sticking point because it makes this approach that I've described difficult to apply. And so the key to solving this is actually to look at a common theme here. Like, what's the common theme with all these analysis? And it turns out it's the admittance matrix. So a few years ago, I think back in 2020, Tom Winslow and I worked on a probe called the WS probe, or the Winslow probe. And essentially what this probe allows you to do is derive the admittance matrix, an accurate version of the admittance matrix, even with feedback around the network. And in doing so, then we can apply probes to your circuit and then derive using math, once we have the admittance matrix, all of the techniques that would have required manual setup. And so this graph on the bottom is just showing, I set it up manually, the technique, and then I computed it with the probe, and you can see they're exactly aligned for all of these different techniques. So that's the value of the Winslow probe. What's inside the Winslow probe? So how does it work? It's kind of like this black box. Well, it's actually very straightforward. It really just builds on the work that Middlebrook and Tian did. And it is essentially this dual stimulus. So we apply a voltage and a current stimulus across the network, and then that gives us the ability to build these terms out. And with some kind of complex math and algebra, we can arrive from these terms at an admittance matrix for this network. So we can apply this probe, and we can then sense the admittance network through the probe. And Tom Winslow describes all of this in his book called General Circuit Analysis Using the WS Probe. So highly encourage you to book. I'll give you the link at the end. So the point is, once we have that, we can derive a lot of these classical results. So this is just showing how to derive the bilateral loop gain, or the true return ratio, from Tian's work using this technique. So the way this works, essentially, we have this amplifier network, or this admittance network. I like to kind of view it like a transistor here, so I put sources and resistors in here. We have a closed feedback loop through it, so that collapses. In other words, the Y22 is in parallel with the Y11, and that sort of simplifies the circuit. And then we can go through this analysis and express this loop gain, or what Tian called the true return ratio, as a set of Y parameters. So it turns out it's equal to this result at the bottom, and then using the probe, since we can derive the Y parameters, all we have to do is run the computation. One interesting thing that comes out of this when you go through the analysis is you can kind of see the issue with the loop gain approaches, which is that the return difference only equals that original rigorous term when the network is ideally grounded, which in a lot of cases isn't true. So if you have a transistor with active sources, usually you have some inductance or something on this. That means that you can't use things like encirclements. This becomes a non-rigorous condition once that happens. So only when that ideal source is grounded is this value equal to the return difference from Bode's work. Okay, so there we have it. Now we're at a simple process for rigorous stability analysis. And all I did here was apply and show you the ADS equations that we can use in the post process in the data display to do that. So the first question you ask yourself, well, first you put the probes as close to all of your active devices as possible. So, and what I mean by that is as in close to the intrinsic as possible. So, for example, if you have a monolithics device, you're already in luck because the probes already exist there and they're inside some of the parasitics. So you can actually get inside the device in the parasitics and they'll automatically give you those results. Then you ask yourself, can you access or turn off the intrinsic sources? And if the answer to that is yes, then you can use either driving point admittance or normalized determinant, depending on how much EM you want to do and how big of a determinant you might need to do. If it's no, then you have one choice for a rigorous technique, which is the driving point admittance, and you can apply it using these equations. And you come back and then you get a quick answer to whether your circuit is stable or not. And based on that, you can figure out what to do next. So if the circuit is stable, you probably want to look over the entire Smith chart, because these rigorous techniques, as I'm going to show you, they're only valid for the static loaded state of the circuit. So like if you have 50 ohms on there, that's all you get. It's the 50 ohm case. You don't get the whole Smith chart like K-factor covers. So you might want to go back and apply K-factor or use another technique after that. If the circuit turns out that it's actually unstable, you want to start analyzing the loop gains, because that's something you can fix. So if you can go find the cause of the feedback that's resulting in the instability then and fix that, you can stabilize your circuit. So then you can also do some other more advanced analysis. So just as an example, I'm going to take the Qorvo GaN, one of the Qorvo GaN devices, and I built a Class J amplifier with that device. And I built it with just using these ideal elements. So these are like ideal microstrip lines, surface mount capacitors, and then grounds here. And when I did, I put my probes on the inside and outside of the device, the gate and the drain, and I looked at the result externally, and I found there's no loop gain, it turns out. So I have no loop gain and everything's stable. So back to the earlier mistake that we had talked about, right? With this type of a circuit, the reason that this is perfectly stable is because every loop terminates with a little ground here. So imagine a signal comes out of this point, this probe point, it goes here, it ends at this triangle. It goes down here, it ends at this little ground triangle. So when you have ideal grounds in your circuit, you're going to get non-realistic stability results. And so what you really need to do is consider the EM effects here, because there's a lot of unintended feedback loops that can occur through your physical structure. So what we do here, we put the EM in, we put the board layout in for this design, and we included the EM, and then all of a sudden we see stability issues come up using driving point admittance. We're not able to turn off this particular device. So we see 3 separate stability problems that come up here. And so we've applied the rigorous method, right? That's driving point admittance, and we see problems. The next question we should be asking ourselves is this an external or an internal loop, right? Is this loop happening inside of the transistor, or is it happening outside of the transistor that's causing the instability? Or is it a combination of both? Because that determines how we're going to fix it. So in this case, if we find that the loop is happening outside the transistor, we need to adjust the board layout. If we find out that it's actually happening inside the transistor, we need to go and adjust the external loading condition that we present to the transistor so it doesn't resonate with the internal loop in there. And in this case, what we found is that there's actually an external loop. So we can look at the bilateral loop gain here from TN, and we see that actually, yeah, there are loop gain spikes at these different frequencies that are causing the instabilities. And so we have to then go figure out where do those loops come from. And a technique that I had proposed, and there's a video link here, you can go watch the video, is essentially to use something called EM circuit excitation. So what we do is we take an EM simulation, and then we take a circuit simulation, and we stimulate the ports on the EM simulation with the results from the circuit simulation. So we excite the circuit. And then if you look at this amplifier, you can see some kind of interesting things. I want to start with the middle plot. That's at 1 gigahertz. That's where the amplifier was designed. So what happens? A little signal comes in, we're looking at the current here, and it gets bigger at the output, and it gets blocked over here at the bias lines. That's exactly what this circuit is supposed to do. So this design is working as intended at the design frequency of 1 gigahertz. However, when we look at the lower frequency at 100 megahertz, we see a big loop gain spike there. And when we do this type of analysis, this EM circuit excitation, you can see where the feedback is actually happening. It's occurring through the bias lines. So that's where the feedback is coming from. That's the loop we need to fix. Similarly, at the high frequency case, there's actually a different coupling mechanism there. At the high frequency case, very little signal is traveling up here into the bias lines. It's actually coming from the ground. So my point is, if you do this type of analysis and you have some idea of where to look, because you already know from your rigorous analysis that there's unstable frequencies, and from your loop analysis that there's external loops, you can then go in and figure out where those loops are using this EM circuit excitation approach. So you can learn more in the video. All right, great. So we've covered that. Now I just wanted to come back around to some more advanced topics. So we rolled this capability out in around, I think, 2020 or 2021, and a lot of designers started using it, which was really exciting. I'm really proud that a lot of designers have been using the Winslow probes and hopefully not getting so stressed out about stability as they used to before. But as people were using it, we actually ran into some conditions where, we wanted to make improvements, and so corner cases or issues with the probe use model. And so what I really want to talk about is some refinements that we've made since we first initially launched the probes. There's three that I'm going to talk about. First one is, we alluded to it earlier, varying load state. Second one is stability margin, and the third one is the ease of use. So let's start with the load state. Driving point and normalized determinant function are only valid for that static loaded state. If we have 50 ohms at the input and output of the amplifier, and we do normalized determinant or driving point analysis, that's all we get. We just see the static loaded condition. We don't know what happens when we change those loads to other places on the Smith chart. To do that, you would need to do a load pull type of analysis where you vary the source and load impedances, which can take a long time and be pretty complicated. But it turns out that with proper application of the probes, we can actually derive the loaded state mathematically from just the nominal case. And Tom Winslow describes this in his book. So essentially what we do is we put three probes here. We put one at the generator side, put one at the load side. So this is like the external points in your circuit. And then inside, even if you have a multi-stage amplifier, inside the circuit, we can put it anywhere. So in this case, I'm going to put it at the gate of the second stage of a multi-stage circuit. And then we just essentially do a set of post-process, and we can compute for those cases all of the other loaded driving point conditions and determine which cases are unstable. So just going back to our Qorvo simple amplifier or a transistor case here, the internal node in this case is pretty trivial. It's just at the gate. So we have an input-output probe, an internal node. We do one simulation at 50 ohms. We run it through an equation. There's a math equation that we apply, and then we get this result, which is on this side is the sources, on this side is the loads. These are all the loads that we swept. You can change this just using math. These are just inputs to a function from the nominal case. And the red points are the points that are unstable. So it turns out for each different source, there's a different family of loads that are unstable, and those can occur at different frequencies. So I just picked one source and one load, and I got an oscillation condition at like roughly 160 megahertz here. And it turns out this correlates pretty well to the original stability circles. So if you look back at the original stability circles, you can kind of see this same trend. But the difference is here, we know exactly what source and load combination are going to produce an oscillation at exactly what frequency. So this is more precise. All right, the second area that I want to talk about is stability margin. So if you go back and watch some of the videos that I made earlier on this, when we were first rolling this capability out, you could see that I picked this circuit where the feedback resistor impacts the stability. And so I picked this feedback resistor value that was like right on the edge of instability here. So if this feedback resistor is 17.6, this circuit is stable. This is normalized determinant method. If it's 17.5, it's unstable. So this, if we're looking at the normalized determinant, it looks like a switch. Here it's off, here it's on, or vice versa. And that's not really the way that we want to be able to look at this. We want to really be able to look at this as a margin. That's the way you should do this. And so Tom Winslow recently wrote a paper where he described how to do this. Essentially, you can decompose these terms, this like H0 term, into left and right hand sides, and you can create these functions that zero out, because this driving point impedance or admittance, those are in ohms or Siemens, right? But if we normalize these things out like we're doing here, we look left and right and normalize them, those terms cancel, and then we can get to these functions that don't depend on absolute values anymore. And we can determine the stability margin in this manner. So we can look at the real and imaginary parts of that. And essentially, we build this function that when it's close to 1, the circuit is is stable, and when it's close to 0, the circuit is unstable. So we can look at it in dBs. And essentially what I did here, I took that same circuit, I swept the feedback resistor, and I looked at this margin, and you can see what's happening in that range where it's unstable. You can see that the result or the response is going down to very, very low dB values, which means that it's getting unstable. Away from that range between, say, like 15 and 18, the circuit is actually pretty stable. So using this, you can determine the margin in stability in your circuit. And the last thing I want to talk about here is the ease of use. So there are things that we can certainly improve in the use model. And the way I wanted to talk about that is Nexus. So the first area of challenge in the use model is that there are actually, we only have one platform, ADS. And so how do you apply it if you're doing like silicon design or something? How do you apply these probes to a silicon design? So Nexus is Keysight's new RF simulator, and it actually spans platforms. So that turns out now, if you're using Cadence Virtuoso or Synopsys Custom Compiler, you can access Nexus as a simulation option. And if you do that, you can use all of the functionality in the Winslow probe in those types of circuits in those platforms. So we've been able to expand the WS probe to multiple platforms through Nexus. And we've also worked on improving the use model here. So what we can do in Nexus is apply virtual probes. So no longer do we need to cut the line and put a probe in there. We can actually just specify or select the node that we want, and it'll apply a virtual Winslow probe there in your circuit, which won't be a component anymore in your circuit, and we can apply this analysis there. The stability margin functions that I showed you, those are built into Nexus, so you can use them. And you can also do Python automation. Nexus is built with automation in mind. So you can do things like set up all of your Winslow probes using a Python script rather than going in manually in the circuit and doing that. And in addition to that, it's built for optimization. So if you want to optimize your circuits or the stability in your circuits, it turns out it's at least 10x faster than classical ADS optimizer. So if you're running a big circuit optimization, you want to optimize it for stability, Nexus is definitely the way to go. All right, just to come back around and close out, I wanted to provide a couple of links. On the left-hand side over here, I've got a link to Dr. Winslow's ebook where he describes all about the probe, talks about how it works. I've also written an app note, so in the middle you can click on this. You can click on this, and you can access the app note, which will describe really how to apply it in Keysight ADS. And on the right-hand side, I made a series of videos. You can go check those out, and if you prefer to watch it in video format, there's a workspace and a set of videos that you can use. All of these are free. The book, the app note, and the YouTube series plus workspace are all free, so I encourage you to go download them and try it out for yourself. All right, back to you.
Okay, now it's time for our question and answer session. My name is Richard Duvall, and I welcome back Fouad, Larry, and Matt, our subject matter experts. Before we start the Q&A, please ask all your questions in live chat. If we cannot answer your question now, we will follow up with you by email. Please also respond to our survey questions. We want to know how we can support your design efforts. Well, I see that some questions have come in, so let's get started. So for Fouad from Qorvo, can you please preview some upcoming Qorvo product releases?
Sure. So here at the discrete GaN product line at Qorvo, we have some interesting products we're about to announce in the next couple of quarters. 4 of these are L-band upgraded products where we're upgrading from 4 to 6 inch wafer size, and these will be form, fit, function replacements of existing products. We're also going to launch 2 medium power, so peak power of 300 watt or so, wider band products. One would be from 1 to 1.5 gigahertz, and the second will be able to cover 2.5 to 3.5 gigahertz. In addition to that, we have high power products, 2 of them in the 600 to 700 watts. And these cover the lower S-band to 7.231 gigahertz and the higher S-band radar band from 3.1 to 3.5 gigahertz. In general, our new development projects that lead to new product introductions focus on supporting customer needs, optimizing the SWaP attributes, and expanding our portfolio by innovating and introducing technology updates. Please keep your eye on our Qorvo website and on our channel communications to receive updates on industry-leading products in the coming future. Thank you.
Okay, thanks, Fouad. And it looks like there are some questions that have come in for Larry from Monolithics. So the first question is, why is it important to have access to intrinsic ports for voltage current waveforms and insertion of WS probes?
So access to intrinsic ports is really important for the following reason. A lot of nonlinear models are encoded to protect proprietary IP and so on, and the classic waveforms that are discussed in power amplifier classes like class A, B, D, F, and so on, these are all really only relevant at the intrinsic ports or right at the current generator. The parasitics of the transistor, like CDS and the output inductance and other package parasitics, actually distort those current voltage waveforms. So if you think that you would optimize the waveform of a nonlinear model at the extrinsic ports, you might really be fooling yourself. And so providing access to the intrinsic waveforms is really kind of critical, because something like class F, which is, from a waveform point of view, is a squared off voltage waveform and a half rectified current waveform, that really is only achieved properly at the intrinsic ports. And so providing those access to those intrinsic ports allows that. The second part of that question had to do with the WS probes, which Matt talked about in some detail. The feedback analysis that is enabled by those is in part really dependent on the stability analysis that's enabled by those is really dependent upon the feedback that's included in the analysis, right? And so if you are only providing those WS probes on the external ports of the transistor, which is useful, you may be missing a feedback loop which is inside of the transistor. And I may have mentioned that in my talk, but I just wanted to kind of emphasize that. And the way that the Qorvo GaN models are set up, you can push in a couple layers and you can see where those probes are conveniently included for you. And in those intrinsic ports, the parasitics are actually external to those probes, and that gives you that answer.
Okay, thanks, Larry. It looks like there's a second question for you, and that is, what is a nonlinear embedding model, and how does it differ from the nonlinear models that we're familiar with?
So the way I think about this is kind of the traditional nonlinear models are capable of doing the analyses that we are used to doing. We can analyze S parameters. We can look at current voltage characteristics. We can look at the IV waveforms that I just mentioned, and we can use that analysis model, if it's properly set up, to look at the extrinsic and intrinsic waveforms. We can also do load pole analysis, and but when we do a load pole analysis, typically we're running a large number of simulations at different load conditions, and then drawing contours, constant power, constant efficiency, and so on, finding the optimal. And that typically requires a number of simulations with that analysis model. With the embedding model, I think of it as a synthesis model in contrast, so that let's say that you wanted to achieve a class F waveform, for example, at the intrinsic ports. With the analysis model, you might have to run a number of simulations under different load conditions to try to optimize that waveform. With the embedding model, you actually can impress that waveform that you want on the intrinsic ports, and with one simulation, you can ask the simulator to tell you what fundamental second harmonic and third harmonic load condition at that particular frequency will actually optimize that waveform at those intrinsic ports. So that's the value of it.
Oh, thank you very much for that. It looks like we have some questions from Matt from Keysight. So it looks like the first question that's come in is, does stability margin provide additional information for the PA designer than stability analysis?
Thanks for the question. The answer is yes, it provides additional information. So if you think about the stability measures that I talked about today, normalized determinant function and driving point impedance or admittance, those are binary functions. So let's break it down. For the normalized determinant function, we measure stability through encirclements of the origin. So the function itself either encircles the origin or it does not. There's no partial encirclement for that function. A partial encirclement says nothing. So we either say yes or no, that it's stable or unstable. For the driving point admittance, we look at the Kurokawa condition. The Kurokawa condition either occurs or doesn't. Kurokawa condition is negative, real part, imaginary part crossing the 0 point with respect to frequency. That either happens or it doesn't. So for both of those, they're binary measures. But the problem is you can have a circuit where the stability is right on the edge, and that will mean that you'll have a binary 0 for that case, but you could be just on the edge of toggling to a binary 1. For example, if the model that you have, if the gain of your model is just slightly off by the smallest amount, that can induce an instability in the circuit. So the stability margin provides a way for you to determine how close you are to this state of instability. If your circuit is relatively stable, if you have a very nice looking stability margin, then you can be confident that as things shift a little bit in your design process, or if you have process variation or things like that, that you'll have very likely continue to have a stable circuit. Whereas if you're right on the edge of an instability, any little change can trigger that binary crossing from 0 to 1.
Okay, thanks. Looks like another question for you, Matt, is do electrothermal effects cause PA instability?
Sure, or I guess another way to look at it is maybe do thermal effects change the stability profile of the amplifier? And I think the answer has to be yes there. So we can look at it in a lot of ways. Let's just start with the idea of temperature in a global sense, right? And we'll go back to the initial model where we talk about stability as a product of gain and feedback. So if you take a device and you change the gain, well, that's going to change the stability. So temperature, we know for GaN devices and for gas devices for that matter, that temperature changes the gain of the device itself. So for GaN devices, if you have a hot temperature, that means that the gain goes down. So conceivably, if you have an amplifier and you have a gain dependent feedback loop, well, if it's hot, then the gain goes down, so you have less gain and you could potentially stabilize the circuit. And the inverse is true. If you go cold globally, the gain will go up. So that means you'll have more gain there, and that could induce an oscillation condition that's not there at room temperature. So globally, there are problems there. You can also look more locally. So if you have multiple devices on a chip and they interact with one another, then that interaction can cause an additional, delay in a feedback loop, and that delay could lead to like a low frequency oscillation. That can certainly happen. And then we can even look at it across a single device. So if you have a single device, or like, for example, a very large device, well, you can have a temperature profile across that device that becomes unbalanced. And that means that like one side of the device is getting really hot and the other side is not is colder. And that imbalance can lead to an instability as well, because it can be, it can actually transfer heat back and forth. It can either cause the one side to continue to get, hot, that'll be like a thermal runaway condition, or it could transfer and sort of oscillate thermally, which will result in an electrical oscillation. So the short answer is absolutely temperature and electrothermal effects can result in instabilities in larger amplifiers.
Thanks, Matt. It looks like your last question is, setting up multiple probes for my design is difficult because there are a lot of transistors. Is it possible to automate the insertion of the probes?
Yeah, it's possible. And in fact, it's especially convenient to do with Nexus. So with Nexus, that tool comes with built-in Python APIs. And so you can go, and we also have in Nexus virtual probes. So you can place virtual WS probes instead of breaking up your circuit and placing them in. So if we combine those two things, that means that you can go through your design. Effectively, you can detect all of your devices in an automated fashion in your schematic using Python. And then you can add virtual probes to all of those nets that touch the device itself. Now for the Monolithics devices, that's not required because the probes are already built in. So you don't have to worry about it if you're using Qorvo Monolithics devices. That already has it. But the other thing that you can do to speed up your stability analysis is you can automate the results part of it, the data collection part of it. So you can go into, for example, and you can create a data display page in an automated way that figures out how many devices you have and how many probes you have and automatically runs the equations for you and does some type of stability analysis. It can either be like, you could tell it, well, is it unstable or not? Or you can also get more fine grained and you can say device by device, which one is, are all of these devices unstable? There's a little bit of repetition if you have a lot of devices in your circuit because you kind of have to repeat equations. So that's a prime candidate for automation. So I think this is a really valuable area to look into, especially if you're working at an enterprise and you have a lot of users with probes on a lot of different circuits. Automation can potentially speed up your design time dramatically.
Well, thanks to all of our subject matter experts for sharing your views on these key questions. To learn more, please go watch the R Circuit Design Boot Camps on Keysight.com. Follow the links on the handouts tab. Thank you for attending this Keysight EDA webinar.